Yes, we still have people logging in, so. Eight. For those of you who have just joined us, we're still deciding on when to start due to people continuing to join the meeting. 30. So Jennifer gets ready, she'll start the discussion.
So I did the introduction. Was I on mute the whole time? I think I might have been muted. I might have given the introduction just to myself. So let's go ahead and get started. I will give the introduction now to everybody. So let's see, a couple of housekeeping things.
I have 1:05. Jennifer, you want to go ahead and get started? Oh, okay.
Couple of housekeeping things. You'll receive an email
You
from
have your
me.
audio up, Jennifer?
and our presenter can't hear me because we're having
I'm not getting audio.
issues.
Yeah, we're not getting your audio. I tell you what, I'll just go ahead and introduce myself. Hi, I'm Steve Cotter with Old Dominion University, and today I'm going to give a brief introduction to implementation of the Quality Information Framework within the RAMI 4.0 framework. First of all, I want to say welcome from the Statistics Division of ASQ to this webinar on the implementation of QIF within the RAMI 4.0 architecture. For this webinar, I'm making an assumption that the average quality practitioner who's logged in has limited or no knowledge of the QIF or RAMI 4.0. In fact, until about I guess about a year ago, I did not start tracking RAMI 4.0, and even later than that, I ran into the QIF, which is an older framework that we'll look at in a minute. So they're relatively new frameworks. There's not a lot of research out there on them. So this really is an introductory session to just introduce you to RAMI 4.0 and the QIF frameworks. And in the end, demonstrate or propose how the QIF can be integrated within RAMI for an architectural approach to quality 4.0. Okay, got to get the focus on the right screen here. So our discussion today, a quick overview of Industry 4.0 and the RAMI 4.0 framework. Then the digitalization framework itself, the overview of RAMI 4.0 in practice, and then the standardization work that's really taking place in Europe, specifically Germany at this time. Introduce you to the quality information framework, just some QIF basics, some QIF technology, and then the proposal for the QIF within the RAMI 4.0 framework, and then finish out with current status and the recommendations. So Industry 4.0 and the RAMI 4.0 framework. As you know, or maybe you don't know, Industry 4.0 evolved out of a 2006 German government initiative to develop a high technology future national strategy. As part of this initiative, the German government set up an advisory board to develop an innovation policy. That working group presented its Industry 4.0 innovation policy proposal at the Hanover Fair in 2011, and it was designed to be a roadmap for government manufacturing to remain competitive in the global marketplace. So Industry 4.0 was adopted by the German government with a focus on development of new business models based on what's termed cyber physical systems. In my research, I've kind of evolved that over to cyber technical systems to delineate technical physical systems from natural physical systems. Let's see, on the bullets here, so it advanced, cyber physical systems and cyber physical production systems. Smart Factory is one of the key associated initiatives. In October 2012, the Working Group on Industry 4.0 presented a set of Industry 4.0 implementation recommendations to the federal government. Then German federal government. Then on 8th of April 2013 at the Hanover Fair, the final report of the working group Industry 4.0 was presented. And the term itself was initially popularized, at least in the literature, that what I've found in 2015 by Klaus Schwab within the World Economic Forum. The fourth industrial revolution represents a fundamental change in the way we create, exchange, and distribute value. It is a technological shift merging our physical, digital, and biological worlds into one, ideally. So note the focus, though, is not on technology. The focus is on creating, exchanging, and distributing value in a new way. The merging of cyber and physical into cyber physical has the role and purposes of providing new value to customers and stakeholders. Most Industry 4.0 research has lost the focus of Industry 4.0 value creation in favor of the technological, the economic, human, and organizational challenges. So we need to refocus on Industry 4.0 research on creation of new value through cyber, what I'm going to term technical social systems. The Boston Consulting Group's 9 cyber physical technologies are probably the most widely published components of Industry 4.0. Various authors have published more components or fewer components, but the Boston Consulting Group components appear to be accepted as the base. In their paper, and this is taken directly out of their paper, you can see the URL at the bottom. So if you can go out and download the paper, the 2015 paper. But in their paper, they stated, now, and this is reading or quoting from them. Now, though we are in the midst of a fourth wave of technological advancements, the rise of a new digital and industrial technology known as Industry 4.0, a transformation that is powered by the 9 foundational technologies advances. And this is where they presented these technologies as Exhibit 1 in this paper. In this transformation, sensors, machines, workpieces, and IT systems will be connected along the value chain beyond a single enterprise. These connected systems, also referred to as cyber physical systems, can interact with one another using standard internet-based protocols and analyze data to predict failure, configure themselves, and adapt to changes. Industry 4.0 will make it possible to gather and analyze data across machines, enabling faster, more flexible, and more efficient processes to produce higher quality goods at reduced cost. This in turn will increase manufacturing productivity, shift economics, foster industrial growth, and modify the profile of the workplace. the key aspect here is Industry 4.0, well, whatever it is, as it's evolving, and it is still evolving in terms of implementation, and it's evolving unequally in different industries and different economies around the world. But it is driving a new, what I call cyber technical social workforce or workplace with massive horizontal and vertical integration. Now, the rest of that, I just submitted a paper for a conference in the fall on Industry 4.0, 5.0 effect on a body of knowledge. And in that paper, I note that a lot of what is out there in publication is still authors citing authors on the promise of Industry 4.0 or the challenges of Industry 4.0. There is, with the exception of the individual technologies presented here, there's the high level management piece of Industry 4.0, the policy piece of Industry 4.0 is still really at the promise and threats stage of discussion. So there's not a lot of good research at the management level on Industry 4.0. Hopefully, my fall paper will initiate some good management discussion. The Boston Consulting Group 9 technologies underpin the 5 Industry 4.0 system of systems themes. Vertical integration and network manufacturing systems. So Industry 4.0 will result in massive horizontally and vertically integrated systems of systems production, ideally. Still in the process of evolving. We're not linked, at least through the value chain. In some cases within an enterprise, we're probably linked vertically, and in some cases within deep vertical system of systems, not completely linked. I know that is the case in some of the work I've done with the US Navy. Horizontal integration through value chain networks, end-to-end smart product lifecycle engineering across the entire value chain. So horizontal integration implies that product and service features will be produced at the most economical point in the value chain and coordinated throughout the value chain, including use and performance feedback from smart products. Now, some of this is starting to happen. As I said, it's happening unevenly, but some is starting to happen. Fully interconnected cyber-physical systems technology. As I said, I use the term cyber technical social systems or cyber technical systems. But the current challenge for industry for this point is the lack of interoperability of legacy Industry 3.0 systems. I've had 2 prior doctoral students do work on interoperability. I still have a current student who's working on interoperability in the healthcare field. And the real driver of the massive horizontal vertical, well, at least the horizontal integration and the vertical integration too, when we look at the RAMI model, is the interoperability challenge. And ideally, the RAMI 4.0 architecture will contribute, will not solve, but will contribute to the resolution of the interoperability challenge. And then finally, new social infrastructures in the workplace resulting in fully integrated cyber physical or cyber technical socio systems. This is key. Implementation of fully horizontal, vertically integrated 4.0 Industry 4.0 will fundamentally change the way humans work and the way production is organized in the future. So this represents a social revolution that will have to be managed. Key term there is managed to prevent economic displacement and disparities. And looking over here, I'm not seeing anything in the chat, so I'll just continue on at this point. The RAMI 4.0 architecture was developed by the German Electrical and Electronic Manufacturers Association to support Industry 4.0 initiatives. with cooperative efforts out of China, Japan, and India. There have not been, to my knowledge, or at least what I found in the literature, cooperative efforts out of the United States. Platform Industry 4.0 was created to promote research in Industry 4.0 for the German industry. They offered an influential reference architectural model, Industry 4.0 or RAMI 4.0, to help organize and identify and classify areas of Industry 4.0 to build foundations for further technological development. So again, coming down to RAMI 4.0, it's a standardized reference architecture framework for Industry 4.0 integrated digitalization. It features common data and information exchange language. It has common communication structures, as we'll see in a minute, and it has cybersecurity and data protection rules. So RAMI 4.0 integrates those 9 technologies of Industry 4.0 in a 3-dimensional layered model that allows technology interactions to be decomposed into smaller and simpler clusters in design. I'll say in design as quotes. So let's take a look at the RAMI 4.0 digitalization framework. This is straight out of the RAMI specification. So it's directly from see what was I think it's the quality details of the asset administration shell. So this is the overall design. It's a 3-dimensional map integrating the data, information, and digital artifacts needed for Industry 4.0. So we have we'll go to the next slide then. We have the hierarchy levels, we have the life cycle value stream, and then we have the business layers. It maps all the stakeholders, so it's not just a technological communications like the Internet OSI model, 7-layer model, although it has, and within the communications layer, it has different layers. It is an overall mapping of the horizontal vertical integration, information and business architectures. So it has 3 basic axes. We'll discuss each one in turn. The architectural layers, this is the business, functional, information, communication, integration, and asset. Notice it goes from the business down to the physical asset itself. So the architectural layer reflects the systems hierarchy from the business policy, which is the customer value proposition layer, down to the productive asset itself. The idea is to link the value created for the customer down to the asset. It also has the life cycle value stream. This in their design is development, production, and maintenance usage. We'll discuss that a little bit more in a minute. But the life cycle value stream, it partitions the standard product life cycle, that is conceptual design, detailed design, scale up and scale out, project management, production, and retirement disposal into 2 phases. That is the type, development and maintenance, and design, the type, development and maintenance, design and development, that's the design and development of artifacts. So the types are generic containers for instances development, and then 2, the instance itself, which is development and maintenance of a product of the physical, or maintenance of the physical product itself. And then finally, the hierarchy levels, the product, field, device, control device, station, work centers, enterprise, connected world, recognizes increasing complexity from the product unit to products to a fully interconnected world. So this is the hierarchy levels. The hierarchy levels, as we indicated on the right, proceeds from the product itself to the product within an interconnected world. The hierarchy levels are taken from IEC 62264, Enterprise Control System Integration, and IEC 61512, Records Batch Control in the processing industries. They represent increasing levels of functionalities and facilities, and it's expanded to include work units labeled product, to Internet of Things, to Internet of Services, which is the labeled the connected world. The life cycle and value stream axis are from IEC 62890, Industrial Process Measurement Control and Automation. Life cycle management for systems and components distinguishes between type and instance. As you can see, type is here, and that is a generic container from which you can develop instances. A type is universal whose parameters can be assessed. An instant is a particular implementation whose parameters will affect only a specific design object. The value stream axis, it has common data and information exchange language, common communication structures, that is network protocols similar to the Internet OSI, and common cybersecurity and data protection. We'll take a look at this later. But the objective of RAMI 4.0 is information interoperability and integration through standardization. So this is the overall life cycle value stream axis. I've realigned it with the traditional life cycle, product life cycle value stream from the conceptual design to disposal and or retirement and disposal. And the point here is that we're proceeding from the customer value proposition through the conceptual detail design, possibly simulation, digital twin. We'll come to the digital twin in a minute, and prototyping to the actual design of the project management, the digitized product information, and the change management instructions and instruction manuals. Those are all types that are filled in with actual instance information. For the instance itself, from a quality perspective, we're interested in the 7 dimensions of quality that can be measured. This is from, I believe, Galvin's work, 1984, widely accepted by ASQ as the 8 dimensions of product quality. And that's measuring and reporting performance. This is what the product is supposed to do: reliability, durability, serviceability, features, aesthetics, where they can be measured in some manner, and then conformance to standards. And then finally, on the instance, the optimization, updates to the instance, maintenance of the instance, troubleshooting, phase out, retirement, and recycling. So the lifecycle value stream axis is divided into the type and instance, and the type is divided into development and maintenance usage. This is in the RAMI 4.0, the instance is divided into production and maintenance usage, so they both have maintenance and usage. A type represents the initial ideal of the product development, while each manufactured product represents an instance of that type. The value stream in the totally digitized production can be viewed, pardon me, can be viewed, hang on, sorry, lost my notes here. Can be viewed in conjunction with the value adding processes, since it enables linking of purchasing, production, planning, logistics, quality, customer and suppliers. In simple words, if a product is in the development state, then we refer to it as a type. Once it moves into production, then it becomes an instance. Whenever a product is redesigned or a new feature is being added, then it again returns to the type state. So let's see, so in this slide, I've related the type instance value stream back to the standard life cycle value stream, from which most of us are familiar from engineering. The 6 layers describe the decomposition of a productive organization into its properties: the business level, the functional level, the information, the communications layer, the integration layer, and then the asset itself. The business layer is the organizational governance policies and processes. For those of you who have studied marketing, these are derived from the customer value proposition. The functions layer, this is the product behavior and functionality. It's the actual y equals f of x transformation in which we embed through manufacturing processes the design product value. The information layer, the necessary information and data. This gives us all the information we need about the product to take it from a type to an instance. In the information and data channels, this is access to product information. The communications layer is equivalent to the OSI internet layer, the 7 layers. The integration, this is where the horizontal and vertical IoT cloud integration takes place. This yields the digitized product information. And then finally, at the asset layer, the asset is either a measurement asset, a productive asset, etc. But it's what creates the delivered product service value. So again, returning to the original intent of Industry 4.0 of creating new value. The layers are designed to decompose that value from the customer value proposition down to the actual delivered or product service value. So let's take a look at the digitized framework. The key to implementing RAMI 4.0 is the Asset Administration Shell, the AAS. It's an interface connecting Industry 4.0 information and data to the physical asset. Under RAMI 4.0, the AAS is a standardized communication interface. Each physical asset has its own AAS, and assets can be logically grouped into a common AAS, so it's totally configurable. AASs then are connected over the Industry 4.0 communication. So this is a visual representation of the asset administration shell, indicating each asset, computer, productive piece of equipment, the interconnection, the server interconnection to the IoT. Each asset has an AAS. And at the process itself, you can group assets into a single AAS. In this case, I've illustrated control, robot, and then the output measurement of quality. And then, of course, smart products will have their own AAS shell. For definition, first of all, let's recognize in industry RAMI 4.0 that the AASs, or our representations, are the digital twins for each asset. I do not know if this is the case, but that digital twin originated from the AAS, but digital twin has grown to carry a broader meaning than just the AAS, but the AAS is the digital twin for each asset. So a digital twin is just a digital representation sufficient to meet the requirements of a set of use cases. Digital representation is all the information that represents the behavior of an entity asset, and behavior is sufficient to effectively lose the ability to distinguish between the digital twin counterpart from the physical asset itself, the product, process, or system. The AAS implements digital twins. It establishes cross-organizational and inter-organizational interoperability. That's where your interoperability comes from, because if you go from a sensor, as many of you know right now, one of the issues that the international, I've forgotten, but there's a lot of work right now because you have different sensors that have different languages that don't even talk to each other. So there's a lot of work now integrating sensor data as let alone other assets. So, but the asset administration shell is the interface. So that you have a single transformation from a sensor language to the AAS, another single transformation from the robot language to the AAS, and they communicate with each other over the AAS. And then the smart product communicates back to the organization on its use via the AAS. So the AAS becomes, the AAS has become the common language in which we overcome some of the interoperability issues. Not that simple if you read the literature. There's still some interoperability issues to tackle, but the AAS is designed to create a common framework for the exchange of information, making a single translation from the asset language to the RAMI 4.0 language through the AAS. Yeah, I've forgotten where I was. I think I was right here. The AAS establishes cross-organizational and organizational interoperability. It covers non-intelligent as well as intelligent assets. It's addressable within the RAMI 4.0 communication network layer and unambiguously identifies the asset. It provides secure controlled asset to all asset information, covers the complete life cycle of each asset, and enables horizontally integrated value chains. And it's the digital basis for autonomous AI products, processes, and systems. So we talk about autonomous robots or cobots. The autonomous robots depend on the AAS or the RAMI 4.0 communications architecture or communications layer, communication through the AAS. So toward global standardization, right now global standardization is being codified primarily through working groups in Germany. And I'm not sure how much China, India, and the other nations are contributing, but this is still being driven primarily out of Germany. The first one is the details of the digital asset administration shell. This is the cover of the book or of the standard. I happen to have the standard open here. You can download it as a PDF. It specifies how organizations can use the AAS to structure and compile asset information. It includes OPC, UA, automation, ML, and RDF mappings. Second document, Steve, idea, got to have my focus on the right screen, is the secure retrieval of CAE data, specifies security requirements for accessing continuous access evaluation data. It's based on exchange of information between AASs. The third document is the access control for Industry 4.0, components for application by manufacturers, operators, and integrators. It describes the attribute-based access control. The fourth document is the administration shell and practices. It summarizes the key aspects of the administration shell, defines generic asset-specific and free submodels, specifies the demonstrator, and helps platform Industry 4.0 validation and implementation of the AAS. And the final fifth document is the I4.0 language, vocabulary, message structure, and semantic interaction protocols. Notice here, again, the I4.0 language architecture is very similar to the Internet OSI 7-layer architecture. So this is how, and this exists at the communication layer. For the actual work is being carried out by 6 working groups. The working group 1 is the reference architecture, standards, and norms. While group 2 is the technology, application, scenarios. Work group 3 is security and network systems. Work group 4 is the legal framework. Work group 5 is work, education, and training. And then finally, work group 6 is digital business models for Industry 4.0. And you can access all of these working groups and the documents through Platform Industry 4.0. Okay, that brings us, so we now have a foundation with the RAMI 4.0 basic model. So the next model that and I happened to run into this, I ran into RAMI about a year ago, and I'm looking at RAMI, okay, this is a sound framework. And for a little bit later, I ran into quality information framework. The quality information framework is an ISO standard CAD neutral file format made for downstream interoperability and traceability throughout the entire product lifecycle, especially in computer-aided processes and engineering applications. It's being developed by the Dimensional Metrology Standards Consortium. And here is the current quality information framework integrated model for manufacturing quality information. This is the QIF version 3.0, so you can see they've been at this model for quite some time. The DMSC mission is to identify urgently needed standards in the field of dimensional metrology and to promote, foster, and encourage the development of interoperability of these standards along with related and supported standards that will benefit industry as a whole. So again, the QIF is tackling the interoperability issue just as the RAMI 4.0 is tackling the interoperability issue. There is, in addition to them, there's also been an initiative, I think the Industrial Value Initiative and the Industrial Internet Consortium also have interoperability standards and approaches. So RAMI 4.0 and QIF are not the only ones, but for our discussion, I think they are the most relevant. I'll propose they are the most relevant. I will leave it up to the community, the ASQ community, to debate whether or not they are the most appropriate, but for implementing quality information. Oops, lost my focus again. Okay, there we go. So QF is a standard which supports digital thread concepts in engineering applications ranging from product design through manufacturing to quality inspection. The key term here is the digital thread. In fact, there is a quality information thread. We'll get to that in a minute. It's based on XML. For those of you who are familiar with XML, it's just a high-level schema that ensures both data integrity and data interoperability in model-based enterprise implementation. QIF 3.0 has been designated as an American national standard, and that occurred in August 2020. And the International Standards Organization, ISO 23952. And here is the link. It's just https qifstandards.org about QIF. QIF supports design, metrology, manufacturing, and is critical to the Industry 4.0 revolution. I took that directly from the DMSC website. Since it is XML-based, QIF can be easily integrated with web Internet of Things applications. And then, of course, again, that's from the About QIF. So this just displays the QIF thread from the MDB through QIF plans, QIF resources, QIF rules, QIF execution, results, statistics, and then back to the product definition. And here, in fact, is the QIF workflow thread. It starts out with the model-based definition. I know that right now, model-based systems engineering, model-based engineering are both hot topics, but QIF has been working on the model-based definition as the basis for traceability of CAD and PMI, or Product Purchasing Managers Index information, CAD shape, PMI, and features. The next step is in the thread is the plans. This is the optional product information. It's the bill of characteristics and inspection plan. Then step 3 in the thread is resources. This is a description of the measuring equipment, information, calipers, CCD vision systems itself, but the resources are the measuring equipment, descriptions of the measuring equipment used to make the measurement. Then there's measurement rules. These are instance templates that can be filled in for like the RAMI had the type, and then it became instance. So these are the rules are really types, and then you fill them in. They become instance templates for how to make the measurements and determination of what the measurements mean. And there's the DMIS. This is the ANSI Dimensional Measuring Interface Standard 5.3 updated to interoperate with the QIF data traceability mechanisms. Then the sixth step in the workflow thread is results. This is actual measurement data associated with the MDB, the model-based definition. And then statistics. This is a reference bundle of QIF result sets. This is where you would output your control charts, output other quality reference rules, say if you're doing runs rules, Western Electric or Nelson's run rules or other runs rules, this is where the statistics output would be assessed. The QIF, we have the metrologist. QIF can be used to transform information between supply chain partners on how and what to measure. Again, this is the horizontal integration, as well as communicate the results from the measurement system within the organization vertically. It also has PLM, that's product lifecycle management software, which is used to track the lifecycle status of a product as it cycles through the marketplace. PLM software is used to manage and track everything beyond the realm of design. And then the PDM is the product data management software, and it's used to manage and catalog product data. These platforms often include version control systems, version history, a feature as well as search features to find components or project data in a centralized database. PDM systems begin and end with product design. So you have the PLM and PDM owners. QF can be used to integrate quality information into the digital thread for manufacturing operations and associate all quality information directly to an information systems master model. And then finally, the metrology software implementers. QIF is an unambiguous, holistic, fully digital standard for metrology information. Will help software parameter implementers in producing or consuming quality data. And I give you the URL for that. So the quality information framework technology, the QIF is coded as we indicated in the extensible markup language. XML is a universal markup language that provides rules to define data, any data. Universal means that XML can be implemented across multiple platforms, thus resolving platform interoperability issues. So like RAMI 4.0, with its communication layer, the XML, use of XML allows the exchange of data across platforms. Unlike programming languages, though, XML cannot perform computing operations by itself. Instead, any programming language, such as PML, PDM, or software can be implemented for structured data management. An XML is both human readable, it's machine readable, it's widely supported. It was one of the, when I studied XML 20 years ago, and when I was still in my doctoral studies, it was widely used then for federated systems, linking different computers together that spoke different languages. So it's made up of XPath. This is a non-XML syntax to provide a flexible way of addressing different parts of an XML document. It has XQuery, a language for finding and extracting elements and attributes from XML documents. It has XML schema definition, describes and validates the structure and content of an XML document. And then, of course, the XSLT a language transforming XML documents into other formats such as HTML, XSL, PDF, etc. So XML, widely supported. It has a history. I know I studied XML 20 years ago when I was doing my PhD studies at ODU. So the QIF elements, each product is fully specified by a QIF document. It's the top level. Notice it's a container. It contains an instance file, the container of all key elements that can be used to describe a product. The QIF library features is an abstraction for referencing product components and parts. Again, it's a container referencing one or more geometrical model elements. For those of you who are familiar with geometrical tolerancing or other elements, QIF characteristic feature of control place, location, specification, tolerance, or other specification. This is a representation of library datums, and DRFs, a collection of non-volatile data structures used to define the geometric controls implied by a geometric tolerance. It links features, datum reference features, DRFs, and geometric tolerances. So again, going back to the previous slide, we have a document. That document has a set of features. In this case, the feature is a whole, and that whole has two characteristics, in this case, position and size, and those are fully described in the document with reference to datum A, datum B, and the diameter. And then, of course, if we wanted to, we could go ahead and add whole roughness features or rim features for burrs, etc. Yeah. Let's see, the product is the name of the element for the MDB data. It ties feature characteristics, nominals, and measurements to the MDB model. This is the digital twin within QIF. The AAS is the digital twin linking the asset, the physical asset that we're using in horizontal vertical integration under Industry 4.0. The AAS is that digital twin that describes the asset. The product feature characteristic nominals measures the MDB model. These are the digital twins in QIF for the product. So application plans, this is measurement specification, high level plan. The bill of characteristics, the watt is being measured. The detail plan is the DRF being measured, the sampling points, the measuring equipment, etc. The application results, again, we have as part of the workflow thread, this is the measurement versus plans, tolerance on product definitions, how feature characteristic measurements are made, stored, and linked to the product definition entity. And it provides a mapping, one-to-one mapping of measurement to product definition. SPC rules can be Western Electric, Nelson Run rules, as I said, your own internal rules that you've developed for your process. So the application statistics, the last step in the the statistics next to last step in the workflow thread, statistical process control rules and results. The statistical method is the SPC rules applied to acquire measurement data. The statistical results are the data versus rule results output. So application resources, this is the measuring equipment that is used to measure the characteristic. Application rules is the measurement process rules. It's the measurement standards, the template, the best practices, the conditions, and any actions relative to measurement results. So that brings us to where I've been going all along in this discussion. How do we fit this thing called QIF within the RAMI 4.0, and more importantly, why? Well, being built in XML, the QIF is designed to be interoperable, independent of RAMI 4.0. By RAMI 4.0 design, the QIF interfaces through the RAMI 4.0 AAS in the communications layer. By RAMI 4.0 design, inter-organizational interoperability is accomplished through the AAS via the communications layer of the RAMI 4.0 model that I showed you earlier. The implications for Industry 4.0, Quality 4.0 design, engineering, and management. Quality system must be vertically integrated into the RAMI 4.0 architecture. Quality strategy must be integrated with Industry 4.0 business strategy at the business level. In the RAMI architecture, quality assurance planning must integrate QIF, MDB, plans, resources, rules, results, and statistics into Industry 3.0 control plans. And I use Industry 3.0 because for those of you who have been in quality for a number of years, we've been using control plans for a number of years, not in the horizontal vertical integration, but in an isolated stovepipe manner. Physical control assets, this is measurement systems, sensors, etc., must be designed and implemented to communicate through the AAS QIF digital twin shell. QIF simplifies integration through XML. Intra and inter-organizational integration is accomplished through the RAMI 4.0 AAS and the communications layer. So this is where I've been going for the whole discussion. The key takeaway here is the implication is that QIF RAMI 4.0 integration resolves cyber-physical interoperability issues necessary for Quality 4.0. This leaves only integration of quality strategy into the business layer of the RAMI 4.0, which is QIF does not do. It leaves integration, and quality specifications. I'm using the Duran model here. Quality strategy comes from quality planning, quality assurance control is quality engineering, where we develop the QIF MDB plans, resources, rules. That's integrated into the functions and into the RAMI 4.0 information layer. And QIF manages the digital twin quality thread or digital twin thread. RAMI 4.0 does not have the quality workflow thread that QIF has. So integration of that within the RAMI 4.0 architecture gives us the workflow thread and then the link back to the RAMI 4.0 communications layer through the AAS, resolving a number of interoperability issues. And that allows QIF to manage the digital quality thread, and RAMI 4.0, on the other hand, it manages the horizontal vertical integration, which really was not designed into the QIF. So in short, and this is my proposal for Quality 4.0 system, vertical and horizontal integration. And my takeaway is that QIF RAMI combined integration provides a structured approach for implementing Quality 4.0. And I want you to think about that because the interoperability has been the real driver of our real or the major, shall I say, impediment or challenge to Industry 4.0 and integration of the QIF XML within the asset administration shell for a physical asset, and then integrating the quality strategy into the business layer and the QIF workflow thread, quality workflow thread into the functions and information layer is and I would propose a useful way to overcome many of the interoperability issues. Now, I say that because there is still research out there indicating that there are some other interoperability issues that have to be addressed, particularly at the discrete measurement level here. And I'm saying discrete measurement level, and that means at sensor levels, taking measurements off machines, because we still have to either communicate through the XML or to the common QIF language, or communicate through the asset administration shell through the common communication layer of RAMI 4.0. So questions, comments? I'll stop talking here. I went too long. I'm at 2:57. Questions, comments? Wow.
Yeah, I have a once,
Uh,
Dr. Cotter, if
do we
you
have
want.
any
First,
questions
thank
out
you.
there, Mike?
Yeah, do you hear me?
I'm not getting your audio. We had this problem before. That's why Jennifer was not able to introduce me. Do you have your mic on now?
Okay, can you
No, I'm
hear me
not
now?
getting your audio. I apologize.
No
There's,
problem.
there's always a
Try this.
technical glitch. I'm not sure what's going
How
on.
about now? Do you hear me
Are
now?
there any other questions, comments in the chat? Oh, you can hear Mike's audio. Well, that's interesting. I cannot hear. Maybe it's me then. Mike, take questions or just type your questions or comments in the chat. Let's have some discussion here
Do you
about this
hear me now?
proposal.
Do you hear me now? Jen, do you hear me? Nobody hear me.
Yeah, I hear you. I think it's just Steve that can't hear the rest
I
of us.
apologize for the technical difficulties.
Okay, I'm just wondering. So first, I would like to thank to Dr. Cotter for a great presentation, and I would like to
Okay, well,
invite
I am,
anybody who is interested
okay,
to
from
join Data
Statistics
Science Interest
Division,
Group, and I have put
something,
that link
chat's
there.
even
Let
acting
me,
up here.
Jen,
Something
is there
following
closed
any of
captioning?
the standards yet? I don't understand the question.
I'm going to.
I think I cut it off. Okay, okay. Uh, in terms of standards, as I said, the the QIF is coming out of DMSC. I just discovered QIF within the last year or so. It's on version 3. I think the QIF was originally QIF View version 1.0 was originally released around 2009, so it's a relatively mature model. On the other hand, the Industry 4.0 work is ongoing, and I'm not sure where the maturity of the RAMI architecture is at this point. But I know it's being driven by the German government, and it has the 6 working groups, so they're actively pursuing standardization of the RAMI 4.0 architecture, at least the communications and the overall architecture. Easy resources to get started. That's uh, yeah, the two I would recommend is right here, the DMSC, log into the DMSC website. I've since, in the last few months, joined the DMSC effort for promoting the QIF framework. And then, of course, come on, get out of the way. Sorry. Uh, the Industry 4.0, thing loose, let me WebEx is driving me crazy right here. Of course, driving me crazy is a pretty short drive. Uh, Going back to RAMI 4.0, yeah, Platform Industry 4.0, there's the address and their contact, and you can just type in Platform Industry 4.0 and download information from them. How to incorporate RAMI with business excellence. For example, Baldrige, that would be, if I recall, Baldrige at the base, and I have to apologize here. I'm going to stop the presentation and file, open, browse. I'll go back to my first lecture. In fact, I just started quality information, the quality systems design class this week, or this last Thursday rather. in summer 23, lectures, quality improvement. Slowing down. So going back to my introductory lecture for this is for students that have, I assume students have no quality background, but going to the national, such as the National Boulders National Quality Award, I would propose that you have the four basic elements. This is of course, the leadership and management side. So that would be integrated into the top layer business model. The human resources functional units, this would be at the functional layer, and then the information and analysis would be integrated into the communications layer. So that would be how we would look at the integration of quality excellence into the RAMI. Other comment? We're 3 minutes over. So yeah, go ahead and thank everybody. Thank you for joining us today. If you have any questions, tcotter@odu.edu or Mr. Miladovich.
Thank you so much to our speaker, Dr. Cotter, and I think that was a great talk, and thanks for putting up with our audio issues. Again, I will send out an email that shows where to get the slides, where to get the recording, and all those technical details. So thanks for attending, and I hope you enjoyed the webinar. Thanks so much.